Okay, so we'll continue. Okay. So I was just reviewing this proof, and it looks to me as if that assumption in the top doesn't is not really required. So you could think on it, but I don't see it being used. Of course, the the inequality, I fixed the inequality here at the beginning of the third line. It was earlier equal to, now it's less than or equal to. For this to hold, we need absolute value here. But apart from that, I don't think the top assumption is necessary here. But never mind. I think can it doesn't hurt either. And this turns out to be the discrepancy, right? And discrepancy of summation over all the of the discrepancies of f on all the rectangles. Now, so we have 2 epsilon is less than or equal to summation over the discrepancies over all the rectangles, which is less than or equal to number of rectangles, which is times the maximum, which is the discrepancy of the function, and number of rectangles uh, at most 2 power c, and discrepancy is this. So therefore, rearranging this, we get c is at least this, where c is the distributional complexity. So that's the bound. So now, if the discrepancy is small, we get that the function we get a lower bound on the distributional complexity. So now, one way is to find functions for which find distributions for which the discrepancy is small, right? So that is what we will see now. And the example that we'll consider is the inner product function. Inner product is just the inner product of two 0, 1 vectors is just summation over all the indices xi, yi, and the summation is modulo 2. So that is the inner product function. So we will, instead of the standard matrix for inner product, which is a 0, 1 matrix, we will consider the matrix Hn, which is Jn minus twice the inner product, the matrix corresponding to inner product. So what this does is, Jn is the all ones matrix. So all the entries, we are subtracting it twice from the all ones matrix. So if a particular entry was 0, it is 1 minus 2 times 0, it remains, the new entry is 1. And if the original entry was 1, so now the new entry is 1 minus twice 1, so it is 1 minus 2, which is minus 1. So all zeros become 1 and all 1 become minus 1, right? So instead of the 0, 1 matrix, we have 1 minus 1 matrix, but the mapping is zeros go to 1 and 1 goes to minus 1, right? You could think of it as, yeah, so that's what you could think of it as, right? So the discrepancy of a particular rectangle, if you are, let's say, you are considering the uniform distribution. Now, instead of number of zeros minus number of ones, or weight of zeros minus weight of ones, now you could just, if it's a uniform distribution, you could just add up the entries of that rectangle, because ones and minus ones, when added up, they cancel each other. So you could just add up the entries of that rectangle, and that is one benefit that we get by this transformation, right? Instead of saying number of zeros minus number of ones, this gives us a benefit. And indeed, we will consider the distribution that we will consider, that we'll work with, is the uniform distribution. So adding up will do. Okay, so now what does the inner product matrix look like? Okay, so instead of the inner product, we are directly going to look at the H matrix. So the H1, right? So it is, the rows are 0 and 1, and the columns are also 0 and 1. So when you have when both Alice and Bob have single entry, so if any one of them have 0, then the inner product is 0. So correspondingly, the H entry is 1. If both their entries are 1, then the inner product is 1. So the H entry is minus 1. And you could very easily see the relation in the third row, third line. It is that the matrix Hn is nothing but can be decomposed into four blocks, three of which are Hn minus 1, and the fourth one is minus Hn minus 1. I leave that as a small exercise. So basically, it is that you can divide the matrix into four sub-matrices based on Alice's most significant bit and Bob's most significant bit. If any of them, the MSB is 0, which corresponds to the three quadrants. If any of their MSB is 0, then the inner product remains the same. The same as in the inner product is just the inner product of the latter n minus 1 entries. If both their MSBs are 1, then it is the inner product is the inner product of the latter n minus 1 entries plus 1. So it will be the opposite of that. So that is reflected here in the fourth in the last quadrant here, or the fourth quadrant here, we have minus Hn minus 1. The other places it is the same. So just think about this. It's a small exercise that I'm sure all of you can figure out. And likewise, H2 is just to see how it is. It is the matrix that is given here: 1, 1, 1, 1, 1 minus 1, 1 minus 1, 1, 1, 1 minus 1 minus 1, and 1 minus 1 minus 1, 1. Right. So these matrices is a specific type of what is called as Hadamard matrices, and it has a lot of interesting properties. In fact, Hadamard matrices are a bit more general, but we will just work with these ones, right? Or these are Hadamard matrices. So all the matrices that we will get in this manner, the number of rows and number of columns, these are all square matrices. The number of rows and columns is actually power of 2, right? Because we have 2, then 4, then 8, then 16, and so on, right? Because every time the number of rows and columns double. So what are these properties? So one is obviously that they are symmetric, that you can see. Each one very, very interesting property is that each pair of rows in Hn are orthogonal. You take any two pairs of rows in Hn, you get an orthogonal. They are orthogonal. So any two distinct pair, the inner product goes to 0. And the next claim is that Hn square, if you take the square of this, you get that it is equal to 2 power n times the identity matrix. Right? So Hn, it has 2 power n rows and 2 power n columns. So Hn square is 2 power n multiplied by the identity matrix of the same dimension. So basically, it is 2 power n. 2 power n is all the main diagonal entries are 2 power n. All the other entries are off diagonal entries are 0. Just as an example, or just as a proof is, if you take h1 square, the proof is by induction. So if you take h1 square, you get this. You can straight verify this. Hn squared, you can verify. It follows by induction, because Hn squared, if you use the previous from the previous slide, if you take Hn equal to Hn minus 1, Hn minus 1, Hn minus 1, and minus Hn minus 1, you can easily get that Hn squared will be 2 times Hn minus 1 squared, 0, 0, and 2 times Hn minus 1 squared. And by induction, Hn minus 1 squared is 2 power n minus 1 times I 2 power n minus 1. So that is what we have on both the diagonal entries over here, times 2, because we are just this 2 just translates. And now we can take this 2 power n into 2 into 2 power n minus 1 outside, both from the first row as well as the second row. What we are left with is I 2 power n minus 1 and I 2 power n minus 1. So which is just basically the identity matrix on 2 power n entries. So it is just 2 power n times I 2 power n. And the last interesting property is that all the eigenvalues of Hn are plus or minus 2 power n by 2. And this is the property that we will exploit here. Why is this true? Suppose V is an eigenvector with an eigenvalue lambda, right? Then we have, you can consider, so Hn times V is nothing but lambda times v. There is a definition of eigenvector and eigenvalue. So now consider V transpose HV, which will be actually uh, lambda times V transpose times V times lambda. So basically, you can, since lambda is a scalar, you can just collect them together. So you have lambda square times V transpose V. But we know that Hn is symmetric. So Hn transpose is nothing but Hn itself, and Hn transpose Hn, which is nothing but Hn squared, we know that it is just 2 power n times the identity matrix. So you can just act as if it was not there. So it is just 2 power n times V transpose times V. So lambda squared V transpose V is nothing but 2 power n times V transpose V. So lambda, since V transpose V is not zero, lambda has to be the square root of this, and hence it has to be plus or minus 2 power n by 2. Right? So all the eigenvalues of this, again, multiplicities we are not considering now, and we don't need that as well. Okay, so now I will state Lindsay's lemma. What is Lindsay's lemma? It gives you an upper bound on the discrepancy, kind of indirectly. Discrepancy with respect to the uniform distribution. Okay, how? Consider any rectangle inside Hn. The difference between the number of plus 1 and minus 1 inside on that rectangle is at most square root of the size of S times size of T times 2 power n. Okay. So again, we'll use the properties that we have already seen. So what are the properties? The main property that we'll use is that all the eigenvalues are plus minus 2 power n by 2. Right? And of course, it's symmetric. Hn is symmetric. So let Hi be the ith row of Hn, and let Hij be the ijth entry of Hn. Okay. Now consider one subscript T, where 1 is in bold, as a vector whose jth entries are 1 if j is in T and 0 otherwise. So basically what this vector does is, it has 1 whenever the j corresponds to an entry in T. So R is S cross T, which means S is a subset of rows and T is a subset of columns. Or you can see both of them as subset of the same index function, right? Both of them as some subset of 1 to 2 power n. And so now one subscript T is a vector which is zeros everywhere except for those entries which correspond to entries of T, and those entries are 1. And similarly, one subscript S is a vector whose jth entry is 1 if j is in S and 0 otherwise. Okay. Now I didn't explicitly define one subscript S, but I'm using that in the next line. Okay. Now consider small x be a vector which is built as a summation of all the rows Hi where I is in S. Alright? So it's a summation of all the rows where I is in S. Another way to see it is, you take, okay, there is a typo here. This H should have subscript n, it should be Hn. Yeah, sorry. So I'll fix that again in the when I share the slides. So you take Hn and you multiply it with one subscript S, and that gives you the same summation, because one subscript S just picks out those rows which are in S. And what do we need to bound? We need to bound the difference between the number of plus ones and minus ones. Right? So now, because the entries are plus 1, difference between the number of plus ones and number of minus ones is just, if you just add up the entries inside R. That will give you the difference. Plus or the sign may have to be flipped, but if you just add up the entries, you will get the difference between number of plus ones and number of minus ones. So all we need to do is add up the entries. How do we add up the entries? You just summation over all the I in S and all J in T, H I J. But now we can see this as 1 subscript S transpose H 1 subscript T. This is because the first 1 subscript S picks out all the rows which belong to S, and 1 subscript T picks out all the columns that correspond to T. And 1 subscript, and since H times 1 subscript S is already defined as S X, now we can replace this part by X transpose. Again, we are using here that H is symmetric. I'm not explicitly written here, but we are using that H is symmetric because we are going back and forth between transpose and the Z. Right? Okay. Now alpha squared, another way to see it is X, the inner product of X and 1 subscript T. Right? The same thing I can write it like this. Is alpha square is this squared, which is at most the norm squared of X and norm squared of 1 subscript T. And what is the norm squared of this? So again, this inequality is by Cauchy-Schwarz inequality. What is the norm squared of this? It is the number of entries. You just do a summation, which is entry-wise squared summation, which gives you. So there are T entries which are 1 and all the other entries are 0. So it's just T, the size of T. Right? So this stands for the size. And this is the norm of X. So alpha squared is at most this. And alpha is the difference between number of plus ones and minus ones. So alpha squared is at most this. And its upper bound, the norm squared of X. So what is X? X is summation over all I in S, Hi. So I'm just writing that here. It is just the inner product of X with itself. I'm just writing it like this. Summation over all I in S, Hi. Summation over all I prime in S, Hi prime. And now I can take the summation outside and inside I can have inner product of Hi and Hi prime. And one thing to observe is that here is where we make use of the Hadamard property that any two rows are orthogonal. So when I and I prime are not equal, Hi and Hi prime, the inner product is 0. So what remains is just summation over single subscript I, because any time when I and I prime are not equal, the value is inner product is 0. So every time for each I we only have the case when I equal to I prime. So we have the inner product of Hi with itself. And what is the inner product of Hi with itself? The inner product of Hi with itself is just, it's all the entries are plus or minus 1. So it is just and because the inner product with itself, it's all the minus 1 will also become positive because we are squaring each entry. So we get 2 power n is the inner product of Hi with itself. And we are adding 2 power n for each I in S. So we have size of S times 2 power n. And substituting this back to the top line, we have alpha squared is at most 2 power n times size of S times size of T. And hence alpha is at most square root of S times T times 2 power n. And that is the difference between the number of plus ones and minus ones. Again, just to recap, Hi be the ith row, alpha is the summation of all the entries in the matrix S cross T, which we write as X transpose 1T, where X is the summation over all the rows of S, which can be written like this. So in fact, one small thing here is that here I think we are just picking out all the columns that belong to S, but it doesn't really matter because the matrix is symmetric. So we pick out all the columns or all the rows indexed S, it's the same thing, except that the resulting vector will be a row vector or a column vector, which is anyway fixed here by taking the transpose. And alpha squared, first we use Cauchy-Schwarz to get this, and the norm of this is nothing but square root of t, so norm squared is size of t. So alpha squared is nothing but norm squared of x times size of t, but norm squared of x is itself size of t times 2 power n. Why is that? Because the rows cancel each other upon taking inner product. The only entries that remain is when hi you take the inner product with itself, and this gives you s times 2 power n. Hence alpha squared is at most s times t times 2 power n, and hence alpha is at most square root of that. And that is also the difference between the number of plus ones and minus ones. Okay, now how does it all relate back to the inner product? So inner product now tells you that by Lindsay's lemma, the discrepancy over the uniform function. Okay, remember discrepancy in the 0, 1 function was number of zeros minus number of ones. But in the translated matrix to plus minus 1, we had number of ones and number of minus ones, which is what Lindsay's lemma calculated. And hence we have the number of zeros and number of ones. The difference is actually equal to the number difference between number of plus ones and minus 1. But it's a uniform distribution. So each entry is actually, there are 2 power 2n entries, and each entry is weighted by 1 by 2 power 2n. So we need to divide. What Lindsay's lemma gave is the difference in the number, and to translate it to the distribution definition, we need to weight each entry by 2 power 2n. So we are dividing it by 2 power 2. Right? This is what we have. Hence the discrepancy. So discrepancy of R is this with respect to a rectangular R. Discrepancy is at most is the maximum. So what is the maximum S can be and what is the maximum T can be? The worst case we can S be everything and T be everything. So S could be of size 2 power n, T could be of size 2 power n. So we have 2 power 3n, square root of 2 power 3n in the numerator and 2 power 2 in the denominator. So what remains is 2 power n by 2 in the denominator. So or 2 power minus n by 2. Hence the discrepancy of the inner product matrix or inner product function is 2 power minus n by 2. And we had already seen that how the discrepancy relates to the distributional complexity. So what is the distributional complexity with respect to the uniform distribution? If you set epsilon to be 1/6, 1 by 6 in the previous theorem, I'm talking about this theorem. If you set epsilon to be 1/6, you get 1/3 here and you get 1/3 here as well, because half minus 1/6 is 1/3, twice 1/6 is also 1/3. So we have the distributional complexity with error at most 1/3 is at least log of 1/3 divided by this, and if you just take the log, you get n by 2 minus log 3, right? Because it's straightforward. And if you remember the theorem that we proved relating the public randomness and the distributional complexity, hence the randomized complexity with respect to public randomness for inner product is also linear. And this is also is at least linear, because here we have n by 2. And the model with private randomness is actually worse than public randomness, because at least you can always simulate private randomness in the public randomness. So the randomized complexity in the private randomness as well is linear, is lower bounded, is at least linear. Okay. So the only thing to note here is Lindsay's lemma gave us the difference between number of ones and minus ones, and what we need is a discrepancy with respect to a particular distribution with respect to the uniform distribution. So we just take the difference in the number and you multiply it with 1 by 2 power 2n, right? And then thus we get the discrepancy of R, of a rectangle R, and by taking the maximum values for S and T, you get the upper bound for the discrepancy of the entire matrix, of any matrix, any submatrix. And this is straightforward. So, like that, we have proved the application using the discrepancy technique. We have proved that the randomized complexity of inner product is linear. Okay, so now we are going to see a generalization. So remember, in the case of Lindsay's lemma, it was just a lemma where we could apply which we could apply for the inner product function, and we had this nice Hadamard matrix and all these interesting properties. Now let us see if we could say similar things for other functions. Like what could we say for other functions? So here we are going to say for other functions which are symmetric. So what do I mean by symmetric? If you interchange Alice's and Bob's inputs, the function value remains the same. Several functions that we have considered are symmetric, like equality, for instance, was symmetric. But greater than is obviously not symmetric. Disjointness is symmetric. So several functions that we have considered are symmetric. Okay. So now let RST be a rectangle. RS cross T is a rectangle. The difference between the number of zeros and ones in R is at most lambda max times square root of S and T, where lambda max is the eigenvalue of the matrix of F. But again, it's the same kind of translated matrix. So you take the original matrix, which is a 0 1 matrix, and you subtract twice the original matrix of the odd ones matrix. So basically what we are doing is the same again. You make all the 0 entries as 1 and all the 1 entries as minus 1. So lambda max is the absolute value of the large eigenvalue with the largest absolute value. Okay, lambda max is the eigenvalue with the largest absolute value, or the absolute value of the eigenvalue with the largest absolute value. Okay, so if you order all the eigenvalues with descending order with respect to the absolute value, lambda max is the absolute value of the first eigenvalue. Okay. So, and what Lindsay's lemma says is actually a special case of this, because the matrix the matrix corresponding to MF dash was nothing but H, which is the Hadamard matrix, and the eigenvalues we saw was 2 power n by 2. And what Lindsay's lemma gave was square root of S times T times 2 power n. So if you take out the 2 power n from the square root, you get 2 power n by 2, which was the lambda max value in that case. Okay, why is this true? Why is this correct? So since MF dash is real and symmetric, the eigenvectors of MF dash form an orthonormal basis for for 2 power n dimensional space. Okay, so basically the eigenvectors of MF dash forms an orthonormal basis. This is a fact that follows from linear algebra. So at the end of today's lecture, I have some 2 slides that give part of the reasons for this, but not the entire thing. But at least for you to get an idea. You may have seen it in some linear algebra course, but I'll just give you a brief idea. But for now, let us move ahead with this proof. Basically, any real and symmetric matrix, the eigenvalues form an orthonormal basis. Orthonormal means they are mutually orthogonal, and they're normal, meaning the norm is 1, norm square is 1. Now let v1, v2, etc. be the eigenvectors of MF dash, and lambda 1, lambda 2 be the corresponding eigenvalues. Okay. So like in the previous case, the difference between number of zeros and ones can be written as so I have again 2 vectors, which one where S is picked out, and one where T is picked out. Okay, so the number of difference between number of zeros and ones is in the original matrix R. MF is 1 S transpose MF dash 1 T, and we can write. And now the next step is interesting. Using the orthonormal decomposition, we can write 1s as summation alpha I vi, where vi are the eigenvectors, and similarly 1t as summation beta I vi, where vi are the eigenvectors. So we are using the fact that they form an orthonormal basis for the entire space, right? And now things are simple. 1 S transpose MF 1T is given by this, is given by, so 1 S and 1 T, I am writing the decomposition for that. And now I am taking the summation out, right? Joint summation I and I prime, alpha I Vi and beta I prime Vi prime. So I can take out the constants alpha I and beta I prime. What we have is Vi transpose MF dash Vi prime, and MF dash Vi prime, since Vi prime is an eigen value, MF dash is the matrix corresponding to that. MF dash into Vi prime, this part, will be equal to lambda I prime into Vi prime. That is the definition of the eigenvalue and eigenvector. So now we have three constants. So we have alpha I, beta I prime, and lambda I prime, and then Vi transpose Vi prime. Again, this is an orthonormal. These are orthonormal vectors, eigenvectors. So this will be 0 unless I equal to I prime. So the double summation becomes a single summation, and the value when I equal to I prime is alpha I, beta I, lambda I, and the inner product of Vi and Vi. But the inner product of Vi and Vi is equal to 1 because this is orthonormal. So the norm of each Vi is also 1. So we are using all the properties of orthonormality here. So the number of difference between number of plus ones and minus ones is given by this quantity summation I, alpha I, beta I, lambda I. Next slide. And let me just take the absolute value of this. This is at most. So alpha I, beta I, lambda I. Now let me just, instead of keeping, I can take lambda I outside by assuming the largest lambda, which is lambda max. So I took out lambda max times the absolute value of summation alpha I, beta I. Now I can use Cauchy-Schwarz to get this second line. It's straightforward. And the last line, this is just the norms. This is just the norm square of the vector which has alpha 1, alpha 2, etc. as the entries. But this is actually alpha I were the coefficients for a decomposition of 1s. And so if you take these coefficients and square it, you should get the same as the norm square of 1s. And the norm square of 1s is just the size of s. And so we have size of s here. Similarly, we have size of t here. So we have lambda max times square root of s times t. Just I will recap. The eigenvalue bound is similar to Lindsay's lemma, but it holds for any symmetric function. So the difference of symmetric instance fxy equal to fyx, the difference in number of zeros and ones for any rectangle is at most lambda max times square root of s and t, and where lambda max is the absolute value of the eigenvalue of mf dash with the largest absolute value, and mf dash is the same as mf, where zeros have been replaced with 1 and ones have been replaced with minus 1. Okay, why do we use mf dash? It's because to compute the difference between zeros and ones in the original matrix, we can just take the sum of the entries in the corresponding submatrix in MF dash. Since MF dash is real and symmetric, the eigenvectors form an orthonormal basis. So let v1, v2, etc. be the eigenvectors and lambda 1, lambda 2, etc. be the eigenvectors. The difference between zeros and ones is this in the first line, and we can write it a decomposition, resolve it using the eigenvectors because they form an orthonormal basis. And this is the thing that we want to bound, and we get this. And what we have is alpha I, beta I prime, and then you collect the summation, and then we have Vi transpose MF dash Vi prime, and MF dash Vi prime is nothing but lambda I prime Vi prime. Definition of eigenvalue and eigenvector, and Vi transpose Vi prime will be 0 when I not equal to I prime and 1 when I equal to I prime. So the summation is just over single variable now, alpha I, beta I, lambda I. Alpha I, beta I, and lambda is at most lambda max, so I take that out, and I have just absolute value of alpha I, beta I, which is at most square root of summation alpha I squared and summation beta I squared by Cauchy-Schwarz. And since alpha I are the coefficients corresponding to the resolution of 1s, the summation of alpha I squared is same as norm squared of 1s, which is size of s. Similarly, for beta I squared, it is size of t. So thus we get the eigenvalue bound. So this can be used to make similar bounds, similar applications like, for instance, what we saw, the inner product bound, which used Lindsay's lemma. However, we should get, this technique requires you to use uniform distribution. So yeah, that's what we want. This technique requires you to use uniform distribution. But yeah, so but then it need not work with several, this need not work with several functions. So, but it may work with some functions. For instance, the discrepancy of disjointness is like 1 divided by 2 per 2n plus 1. So when you apply this technique, what you end up getting is nothing but is a logarithmic bound, which we know is not good. So yeah, so disjoint, there are functions which doesn't do well with this technique. Right now, I just want to give you a brief overview about why real symmetric matrices are special, why they have orthonormal decomposition, and why so one is that they form an orthonormal decomposition, the eigenvectors, and two, the eigenvalues are all real. Why is that? So first, the proposition 1 is easy to see. The inner product of A, V, and W. Let P and W be any two vectors. This is nothing but V transpose A transpose W, but A transpose A, so we can write as V A W. Okay, proposition 1 is used to prove proposition 2. If V, W are eigenvectors with different eigenvalues, then they are orthogonal. Why? Let AV be L1V. So that is the L1 is the eigenvalue corresponding to V and L2 is the eigenvalue corresponding to W. Then L1 of the inner product, L1 times V comma W is equal to, you can take the L1 inside. L1V is same as AV, right? Because of the eigenvalue property. And by proposition 1, we have AV comma W is the same as inner product V comma AW. And AW is L2W because of the eigenvalue property. And now we can take the L2 outside. So we started with L1 multiplied by the inner product and we ended with L2 multiplied by the inner product. We know that these L1 and L2 are distinct. So it has to follow that the inner product is 0, right? So this gives you an indication that the inner products, the eigenvectors are orthogonal. But only for those eigen vectors that correspond to eigenvalues that are distinct. Now, for in a real symmetric matrix, we could have repeating eigenvalues, the same eigenvalues occurring multiple times, but that requires a different treatment. And that is not immediate from this. But this gives you, and I hope this at least gives you an idea for those eigenvectors with different eigenvalues. You can look up the other proof, other part also. Okay, now the third property, which I don't think we use anywhere, the eigenvalues of A are all real. Why is that? So just before this, let V be an eigenvector and L be the corresponding eigenvalue. And by here, the V superscript star is what I mean. What is a Hermitian, which is you take the transpose and complex conjugate. And we did not have to do this till now. So it's kind of the equivalent of transpose in the complex world. So you take the transpose and conjugate. So first we have L of V comma V star. So this is the squared norm of V for a V with complex entries. Squared norm of V. Now I can take the constant inside, that is L. LV is AV because of the eigenvalue property. Now by property 1, I could move A to the V star. So V comma AV star. Since A is real and symmetric, now AV star is the same as the Hermitian of AV the whole star. Doesn't matter. Is it easy to see? Because of course the conjugate doesn't matter, but the conjugate doesn't matter, but does it? But AV star is V star A star, but V star A star. So I may need to just think about it. I think there is some issue here, but it's. I don't think it's something that you cannot sort it out. You cannot figure out. So basically, AV the whole star, where now AV is equal to LV because of the eigenvalue property. So we have V. What comes out is L star, and hence L of V star is equal to L star times V comma V star, the inner product. Since the inner product cannot be 0 because it's just a squared norm, for this to be 0, the vector itself has to be 0. And hence, because of that, L has to be equal to L star. So the Hermitian of a scalar is nothing but the complex conjugate. So if the complex conjugate is equal to the number itself, that means the number is real. This shows that the eigenvalues are real. Just think about this and sort it out, or we could sort it out in the discussion session. And that is about it. So we just to recap, we started with this distribution of complexity. The application was to show lower bounds for the randomized complexity, and we introduced the notion of discrepancy, which is roughly the number of zeros, weight of zeros minus weight of ones, and what is the maximum that happens in any submatrix. And we had this discrepancy based bound where for matrices of low discrepancy or functions of low discrepancy, this gives you a better bound on the distribution of complexity, right? And we saw the proof of that. And inner product, we consider inner product, and we translated matrix where 0 was translated to 1 and 1 to -1. We considered this and we showed that the difference between 0 plus ones and minus ones, or zeros and ones, is at most something, size of s, size of t times 2 power n. This bounded the discrepancy to if you take s to be the maximum, t to the maximum, and thus we got a bound on the discrepancy and hence a bound on the distributional complexity and hence a bound on the randomized complexity. And we showed that the randomized complexity of the inner product function is linear. We generalize the same thing to any symmetric function. So instead of square root of s, square root of s times t times 2 power n, we have square root of s times t and multiplied by lambda max. So lambda max is outside the square root, which is the absolute value of the eigenvalue with the maximum absolute value of the translated matrix. Again, we need a translated matrix so that we have the nice plus minus 1 property. Again, the proof is very similar, and we also observe that this is a generalization of Lindsay's lemma because lambda max was actually 2 power n by 2 in the case of the Hadamard matrix. And we concluded with the some indications of why real symmetric matrix have orthonormal eigenvectors, right? And yeah, that's about it. Okay, thank you.